since we weren't doing that today. So I'll go ahead and go back to recording. Happy Friday.
And then with all the craziness, I saw some of you with the roll of the eyes when I said you just had a hard day today. So hang in there, one period at a time, okay? Some of you guys have at least one more test to take today. That's what I said. Okay. If you guys don't mind burning cry, I'll do the best I can. Try to lead you through so that we can get section 3.2 done. You guys don't need to really skip any lines, but I do want you to grab out your calculators really quickly and make sure that you know where the log button is and the ln button. These are two special types, not the only two, but two special types. And plus some of you guys, your calculators, the older ones, they're not going to quite be as cool as the newer ones for logarithms. So I do want you to look at that as well. So calculators out. I'm going to get my calculator out as well. Or I should say open. I want you guys to try the following. If you find where the buttons are for common log and natural log, which are what these two are, I'll put the names down. Because I'm saying them, aren't I? Common log. And natural log. These are functions like square root that need you to put something into them. If you just hit the log button and hit enter, what happens? If you just hit the log button and hit enter. Yeah, because you have to put something inside of it. It's log of something, ln of something. So I want you guys to just start with log, not ln, he's a little messy. Start with log. I want you to start plugging in whole numbers, no fractions, no decimals. Start plugging in whole numbers to log, and I want you to see if you can figure out which one would make the answer 1. Start plugging numbers into log. Which one would make the answer 1? Ah! How'd you find it so fast? If you get, or if you try the 10, you're like, oh yeah, it does work. Why don't you try it with ln? But I'm not going to say whole numbers anymore. I'm not going to say whole numbers anymore. What number plugged into ln would make it 1? It's not 2.1, but it is 2.71828. You have to keep on going. Otherwise known as E. Why don't you guys try that? ln of, can you find the E on your calculator? Yeah, there's two different places. One of them is e to the power of, and that second ln, you have to put e to the 1. Or the other one, is it the division sign?
Yes.
Okay. Or the division sign. So far, hopefully, you guys have already found, where's my calculator? He's not coming up. Come on. So far, hopefully, on the left-hand side of your calculator, you've seen the log and you've seen the natural log. I'm on my graph. Let me get to the home screen. And you figured out that log of 10. Hey, do you guys see what is above the log? What's the blue above the log on your calculator? Ah, it's 10 to the power of. It's like a little baby reminder. Log of 10 equals 1. And then ln of, you guys said e, which is second divide. But wait a minute. Who's in the blue right above ln? E, it's a little reminder, is 1. So what on earth is a logarithm, and why does common log of 10 equal 1, and why does ln of e equal 1? But if you plug in almost anything else, hold on. Can anybody think of another, and maybe you won't be able to think of it, maybe you just trial and error it. What's another number plugged into the common log, log, that would have a nice, even, whole number? 100? What? I think that's pretty hard out. What does it equal? 2. What would be another one?
1,001.
Okay. Why are these the nice ones? What's the third power?
10.
10. So if you plug in 10 to the 1, log of 10 is 1. If you plug in 10 to the 2, or 10 squared, you get 2. If you plug in 10 cubed, you get 3. What do logarithms find? Exponents. Logarithms solve for exponents. I can show you this with ln also. It would just be kind of messy because it's not a nice number. ln of e we know is 1, right? Okay. How would I get 2 then?
E squared.
Yeah, I would do E squared. Oops, lots of messy parentheses, lo siento. There you go. 2. How would I get 10? E to the 10. A logarithm says, give me something with an exponent and I'll tell you that exponent. Now, hold on. What if I was to plug in something like, ready? Log of 27. That's not 10 or 10 squared or 10 cubed or 10 to the 4th. So why on earth is log 27 1.43136376? What does that mean? Second log. What happens if I raise 10 to the power of this guy? What do you think? You should get 27-ish. Remember, the calculator had to round. So close. They would just keep on going forever. So whatever you put into a log, represents a second log. The power that you would need to raise the base in order to get that inside number. Now hold on. Let's come back. Common log never has a base written. But have you guys figured out what base we're talking about? 10. Common log has a base of 10, we just never write it. Think of like our number system is based on tens, like ones, tens, hundreds, thousands. Kind of a reason why we have the common log being of a base of 10. ln, what's his base going to be? Now the weird thing is ln has his own special notation. He's called natural, well basically without going into tons of detail because he naturally occurs more often than the common law. E naturally occurs anything from radioactive growth or decay, to population growth, to, what else does E come up? Compounded interest. E shows up in all sorts of different ways, just naturally occurring. It's kind of weird, kind of like pi. Pi shows up in circular dimensions and ratios. Anyway, so since this log has a base of E, it happens so much, and it's so special, they actually gave it its own notation. Just think it starts with L because it's a logarithm. That's how I think of it. Like, oh, they wanted me to know it was a log, and then put the N, I don't know. I'm sure there's a much deeper explanation as to why it probably goes back to the Latin or something, but it's just referring to the natural log. Yeah, Chris, what was that? Okay, so that's who these guys are, but we're going to dive a little bit deeper into what they do. But I just want you guys to get the idea that a logarithm really is just saying, okay, what power? Okay, what exponent? But of who or of what? Of the base. Now hold on, can we change the base in our calculator to something other than 10 and other than E? You can? How? Come on, some of you figured this out last year. Would have made it a lot nicer on that test. How do you change the base to a logarithm to be something other than E or other than 10? As long as you have a calculator that doesn't have the old yellow button, you should be able to go, where's my mouse?
To math, this is log base.
Yep. Go math and go down to log base. Now, if you have one of those old calculators with the yellow button, I am so sorry your programming does not allow for you to have this. But there's a snazzy formula that you can kind of cheat and use and be able to do it. But for the rest of us, there's a bit of a delay. There you go. Log base, letter A. What does that let you do? Give the base. So let's say you had something like, I don't know, 32. Is that going to be a nice number if I have a 10 down there?
No.
No! 10 to a power does not equal 32. It's not a nice power. How about E? No. But what can I break 32 down into being a power of? Maybe 4. 4 times 4 is 16 times 4 is 64. No, 2. 2. And how many times? I don't know. I don't want to factor. Okay, it's 5. Cool. 2 to the 5th. Oh, that's spiffy. So what if you had something super nasty, like, I don't know, 256, and you were supposed to, like, do a factoring tree and break them down? Couldn't you say, I wonder if 2 goes in evenly? Couldn't you throw 256 in and be like, what would be the power? Oh, it's faster than a factoring tree. Maybe
2 to the power of 8. Anyway, pretty snazzy. If you did have to break a number down.
And you have had to do that in the past. Okay, so you can change the base. For those of you poor guys with the yellow button on your calculator, you have to wait until we get to something called the change of base formula. Then you'll be able to do it too. Let's talk about a logarithm, just like we did exponential. The key parts. Well, first of all, there's the log, but that's kind of like a square root. Yeah, well, you have the square root. Well, you have a log. Okay, it's there. It's there. It is what it is. But what are the pieces inside the log? Well, A is going to be our base. We just talked about how every logarithm solves for a power, or solves for an exponent. So what the log equals, or y, is really just the exponent. It's just finding the exponent of the base. It's just finding the exponent of the base that gets to x is the argument, that gets to the argument. Now, last year you probably talked about this conversion between logarithmic and exponential because they are so closely tied. A logarithm says, let me take this number, let me break them down into, for this base, what the power should be in order to equal. So we can actually convert from one to the other. From this would be called logarithmic form to exponential form. If you're a highlighting person, grab out a highlighter. If you're a starring person, get ready to star. Because it's very helpful to know how to visualize how to go from logarithmic form to take the base to the exponent to equal the argument. I like to think go back and forth if you're doing it a shortcut version. Take the base, when you go to exponential, base to exponent equals. I just go back and forth across the equation. Base to exponent equals x. But this is a conversion that you guys, I think, talked about last year. This one would be called, technically, our logarithmic form, because it has a log. And this one would be called our exponential form, because it has it written with exponents. They mean the exact same thing, but our brains don't think in logarithms so good, or I should say so well. So sometimes it's helpful to take something that's given to us as a log and to write it as an exponential. Now, kiddos, as you come down here to where it says, hey, let's learn to use our calculator, I've actually already kind of had you guys working with your calculator today. So let's not use our calculator, even though I know you have the log base button, yada, yada, yada. But my question to you is, hold on, haven't we already done the log base 2 of 32 one? And some of your classmates can't even use that cool log base thing. Well, is this one that you could actually solve without a calculator? Yeah. Because we could take 32 and we could rewrite him to be, well, by breaking down like I did on the boards that you saw yesterday. We could break him down by hand to see that he's 2 to the, sorry, I should have written 2. 1, 2, 3, 4, 5, right? So if I'm saying 2 to what power is 2 to the 5th, what's the final answer going to be? 5. The log just says, what's the exponent? But for those of you that have the nice updated calculators, yes, the log base would have solved that for you if it had been nasty. And for those of you guys with the yellow button, technically how you would do it is using a change of base formula, just hang in there. And I'll show you how you can use your common log or natural log to solve this also. But kiddos, let us see. There's someone with the log base button, or maybe multiple ones of you. Can you plug in log base 4 of 2? We haven't done that one today. Log base 4 of 2. Can you tell me what it is, and then we'll try to work backwards as to whether it makes sense by the math. 0.5, we've already gotten an answer, and that's totally right. 0.5, or that's the same thing as 1/2, right? Yeah. Okay. Why does it make sense if we plug in 2 and a logarithm finds a power of the base? Why does it make sense that that would be 1/2? Not 4 divided by. Good idea. Not 4 times. Even though it's true, that's not really what's going on in this one.
Because let me show you something else that's 1/2. That's 1/2 also. And that's not times 1/2. That's not divided by 2. So what is the 1/2? I saw some hands. Aiden. Because this would be the same thing as the square root of 4, which would be the same thing as 4 to the 1/2. Those of you guys that were thinking dividing by 2, it doesn't work on this one. But question, does the square root idea work? Because it would be the square root of 9. For those of you that are like, where on earth did this problem come from? I made it up to tell you that 1/2 doesn't just come from this. 1/2 could also come from that. This would be the square root of 9, which would be 9 to the 1/2. The 1/2 comes from the exponent, comes from the power.
I just don't see the connections between numbers like the letter A, obviously, where 32 and 2 and 5
Oh, 32, sorry, 32 is equal to 2 to the 5th. I divided it by 2 5 times. So I was able to substitute 2 to the 5th in, because the 32 was supposed to go in. I plugged in, I substituted for 32, and then I was able to say, oh, hey, steal the exponent. Just like here, steal the exponent, steal the exponent. So a logarithm solves for the exponent, like we saw in our calculator a second ago.
It's been a while since the nice ones, though. We did some nasty stuff first, but if we were to come up to where we were doing the tens, I think that's the one that's easiest to see. You can kind of see it here with the e's, because I just passed by them all, sorry. It's still going. It's not me. I'm just waiting for it to stop. Stop. Thank you. There we go. Base is 10, 10 to the 1, log is 1. Base is e to the 1, log is 1. This one, base is 10, 100 is 10 squared, log is 2. Base is 10, 1,000 is 10 cubed, log is 3. Or these might be even easier to see. Base is e to the 1, 1. E to the 2, 2. E to the 10, 10. So whatever the exponent is of the base, as long as it matches, will be the answer. Now, don't worry. As long as what's down and what's up. As long as the base of the log and the base of the exponential, as long as they match, the exponent will always be the answer. But let's develop that one, because this is really just an introduction. So, have you guys at least highlighted this conversion between logarithmic and exponential? Okay, highlighted box something or others. Okay, the conversion between log and exponential. Long story short, every log is saying, give me a number, and I'll try to figure out what exponent that base would need to be raised to. Give me a number, and the log tries to figure out what exponent the base needs to be raised to. So, let's do some more examples. Let's get a little further into the There we go. Oh, I'm going to help out people with the yellow buttons on their calculators. Okay, hold on. Change the base formula. Let's get this first. If you need log base, I'll do an example down here, but log base, we'll just call it B for right now. So I think we called it A on this stuff, right? Okay. If we need log base B, we can change it to be any other log we want using the formula of dividing log of the new base of the argument over log of the new base of the old base. Now, this isn't going to look all that spiffy or all that helpful unless people with yellow buttons on their calculators who don't have that spiffy log base button realize, well, I can take one of those nasty bases and I can say, well, hold on, I don't have a log base button, but I do have a common log. They could plug in a common log and they can get the exact same thing by using the common log and dividing. Or they're like, oh, but I have an ln button. They can solve for the exact same thing by using the ln button and dividing. So then those of you guys that were able to plug this into your calculator, it was no big deal. Just log base 2 using the math feature of 32. You solved it. It was 5.
But people without that would have needed to go back to either the common log of the 32 divided by the common log of the 2, or they could have gone to ln of 32 over ln of 2, using this pattern of stealing the argument for the first log or the top log, stealing the base for the bottom log. And all of these plugged into the calculator all equal 5. So those that don't have the log base, you just have to know a formula that, don't worry, the others will have to know as well for other problems. But you would need to use the formula in order to be able to solve. We could do C, but I think A is enough. So those of you with the full log base, you can plug it in, no stress. For those of you with just common log or just natural log, you just have to use this formula to say, all right, cool, I'll take my common log or my natural log of 32, I'm going to divide it by my common log or my natural log of 2, and everybody ends up with the same value or the same answer.
Alright, I would star and highlight this one too. It's one of those formulas that I know you saw last year, but most of you totally forgot. And that's okay, it pops out of our minds really quick after a test. So you're definitely going to need to study it again. Okay? Alright. Now let's start getting into our puzzles for logarithms. To get into our puzzles, this will help some of you guys that I was introducing these properties when I was doing some of the examples, but let's go ahead and write them down. The properties can help. They're like little baby formulas for logarithms. Little baby formulas for logarithms. Technically, you can also use your logarithmic to exponential conversion that we started earlier today to rewrite, and you'll also see why this is true. Because the first property of logarithms, any log of 1 is always 0 because when you switch the form, base of a to the 0 power will always equal 1. And that one makes sense in our brains. We're used to seeing that. Doesn't mean we always get it right, but we're used to seeing anything to the 0 power is 1. Except for 0 to the 0 power, that doesn't work. But any non-zero number raised to the 0 power is 1. That one makes sense in our head, but we have to now say, hey, there's a logarithmic way of saying that exact same thing. In our heads, a to the 1 equals a makes sense, but there's a logarithmic way of saying the exact same thing. Log base a of a to what power is a? Oh, 1. So to train our brains to look at logarithms. Maybe not as familiar. We might not ever get as familiar with logarithms as we are with exponential, but if we can go back and forth, then maybe that'll help us out. These last two are pretty important, the inverse property and the one-to-one property. I'll give you a second to write those down. We're going to practice those a lot today as we go through and do some examples. I'm going to stop talking so you guys can catch up. On the examples, I don't know, skip me one line each? Not even one. Actually, I don't think you need to skip any lines at all. Okay, for numbers 3 and 4. It's a little hard to see, and we'll talk more about this as we go further on. But logarithms and exponentials are inverses of each other for the very reason that you guys saw, well, you saw when I plugged in something like ln of e squared and the answer was 2, or
log of 10 to the 4th, the answer is 4. Whenever you take a log with a base that matches the base of the exponential you put in, everything is always going to get undone except for what's in the power. Log base 10 of 10 to the 4th, everything's going to get undone except for the power. The reason being is because the log and the exponential, in a sense, cancel each other out, undo each other. So if I was to give you something like log base 4 of 4 to the 8th, what would the answer be of this one, guys? 8. Yeah, it would just be 8. Whenever you have a log base and an exponential of the same base, it can always cancel out by this inverse property. And that works when you take a log of a base a of a to the x, getting just x, but it also works the other direction. Remember inverses, you can take f of g or g of f, you can go either direction. You can put a log inside an exponential. And once again, they'll cancel each other out as long as they have the same base, because they are inverses of each other. And last but not least, this property is the one that hopefully you guys even understood yesterday with the exponentials. If we can make the bases match, which with logarithms, the log bases match, then we can just steal the arguments. As long as there's nothing else being added or subtracted or multiplied, if we have two logs on either side with the same base, and that is all, then we can go ahead and just skip. We can ignore the logs and go straight to the x1. Number 3, the whole thing is super important. Number 4, the point is you can ignore the logarithms as long as the bases match. And you just have x equals y. Let me scroll down a little bit. Let's look at A, B, and C. So, without even going to the calculator, kiddos, don't the bases match? So then what can I say? Because a log says, hey, what power of 11 is 11 to the 7? Oh, 7. But the inverse property, another way of looking at it, is log base 11 of 11 to the 7. Since they're inverses, all of this gets canceled, only 7 is left. How about letter B? Pi to what power is pi to that? There's nothing there, we assume it's a... Careful. If there's nothing there, we assume, well, it's there. Pi is there. It's not gone, so there has to be at least one of them. It's pi to the 1. So pi to what power is pi to the 1? You're right, they do cancel, but you have to keep the exponent, which is 1. Ooh. What about letter C? How are we supposed to visualize? Any log of any base of 1. Look at property number 1. What's it say? Any log of any base. Because 3 to what power would be 1? Oh, anything to the 0. Okay, those are just using properties. That's not using your calculator, not using any crazy tricks necessarily. It's just, remember this whole chapter filled with puzzles? We just gotta know the rules. So let's see if it gets any harder. Ooh. Ooh, that looks awful. It's not bad. Look at the one that we found. This looks awful. Way more complicated, but wait, look at the one-to-one property. There's no addition outside the log, no subtraction, no multiplication outside the log. Just look at the logs, and what do you see? Same on both sides. So look at the one-to-one property. What can we do if the logarithms match? Technically, we're not canceling because we're not raising 10 to the power of. That would be a way of canceling. But we can ignore them and make what statement? It's just like yesterday on the whiteboard up on the football field. Except now, instead of having bases raised to powers, we steal the powers and ignore the bases. Now we have logarithms that match. We ignore the logs, we can set the arguments equal. To solve, we just use algebra, right? Subtracting the 1. Ugh. And solving for something nasty, that's totally right. As long as I wrote it right, yeah. So, one-to-one property isn't bad either. Just you have to keep an eye out for it and say, oh hey, the logs match. I can make this huge jump, which makes everything so much nicer. If only you remember your property. As long as the logs match, we can ignore them.
if there is no addition or subtraction or multiplication going on outside the logarithms, as long as the logs match, you can ignore them. Steal the argument, solve. So was this one really that much harder?
No.
I don't think so. I just kind of threw you off at first when you saw the 3-1 nasty equation all of a sudden. On our calendar, let's talk about our calendar really fast. I think I have it open on the screen. We got kind of half a day off from section 2.7 not being able to get totally done. Remember, we only got to do part of it on that Friday before break when you guys had retreat. So here's the struggle. I had split section kind of just for the purpose of having time to do homework questions on section 2.5. This is not you. This is not helpful. This is way beyond you. Hold on. Don't worry. Don't worry. Don't worry. You're like, what? We're not even doing trig yet, let alone inverse trig derivatives. Okay, here we go. We were supposed to do section 3.2 the second half today. But what did we do? First half. We're half a day behind, literally. We're half a day behind. So, here's what we're going to do. There are technically 2 different homeworks from the exact same section, just because I said, like, oh, well, if I'm splitting it up in 2 days, then you can actually do all the homework for one part before I cover the second part. So I split it up so that you could do it in little pieces here and there. Struggle is, we lost our half day. So what I'm going to do instead is we're going to start taking notes on section 3.2b. Let's see how far we get. I'm still going to keep the homeworks as 2 separate numbers, just because on my homework page, this is usually how the calendar works out. Just sadly, this year it was weird with all the minimum days and the retreats and then the PSAT and then, Precalc when you shake out, why not? Let's throw that in there too. So let's go ahead and let's get into section 3.2b just a little bit. We probably won't finish it. What is due on Monday? Look at the board. Homework number 19, which is section 3.2a. So what we cover in section 3.2b, that homework will technically not be due until Tuesday, but I bet from what we covered today, if you're already caught up on things, if you guys have been doing really well, watched the video last night, had your notes ready to go, you could probably do both sections and have 3.2 pretty much out of the way. For the rest of you guys, as you start taking notes, I'm going to pass out tests and give you correction papers as well, but we're not making a new section, okay? We're not making a new section. It's just the second half of 3.2. So stay in 3.2. Don't make a new title. Don't make a new heading. But in your mind, originally I had it split so that we could, if we weren't half a day behind, we would have finished 3.2a at the end of yesterday. That homework would have been due today. 3.1 would have been done the day before. It would have been due yesterday. So let's get these notes started and let me get these corrections out. Before I pass out corrections, take correction papers out. Some of you guys are getting close to finishing this up, so I'm going to fill in just a few things before I start passing out those tests. I know. I don't know why. It's worse than normal. If you guys remember, exponentials had the point 0, 1. If logs are the inverse, everything switches. So logs are going to have the point 1, 0 instead, which will always be its x-intercept. Exponentials had the point 1a. Logs are going to have the point
A1. Which I don't know where A is. It depends on the base. If it's 2, it's really close. If it's 8, well, it's really far. But I am going to have the point A1, whoever A is, but 1's going to stay the same. No, not the steak sauce. And then, exponentials have the point -1, 1 over A. Logarithms are going to have the point 1 over A, -1. Everything just flips. You can get the points down for one, you can get the points down for the other, as long as you switch the x's and the y's. Now, there's one other thing that switches, but the points don't necessarily show us what it is. Exponentials swooped up really steeply, like a U. Exponentials swooped up and had a horizontal asymptote. Logarithms, when you switch it, are going to swoop up also, but at a very different curve and have a vertical asymptote. It has an asymptote also, but it has a vertical one. So a vertical one, because think, the x and y switch. So y equals 0 is for exponential, x equals 0 is for logarithmic. The range is going to be, for exponentials it was limited, but for logarithms it's going to be like the domain of the exponential. It's going to be unlimited, negative infinity to infinity. Domains and ranges switch too. The domain is going to have the restriction that exponentials did, only 0 to infinity. Strictly monotonic, it is strictly increasing, just differently. But it's going to be much slower at getting up than the exponential. Exponential just zooms up. Logarithmic, it takes its time. Quite literally. It increases, but much slower, and it's continuous, just like the others. Alright, get that page down. This is the parent function for logs. This is the parent function for logs. Those that need to catch up in 3.1 notes, you're going to be taking notes on transforming exponentials. Just think in 3.2, when we come back on Monday, we'll be transforming logarithms the same. Shifting, reflecting, taking the points and using them, using the asymptote also to help us out. So 3.1 will hopefully help you with 3.2 also. When I call out your name, this is in no particular order. Come on up and grab your test. We did have A's, we did have over 100s, but we also had on the other side as well. Correction is the other side. Instead of the A's and the 100s, the other side would be
0?
no zeros. So counting. Everyone got at least a 30. I made up these corrections will, remember how I said we're saving it, we didn't do corrections on chapter 1, we will let corrections be bonus on this one. But remember, we already did the half, so what's next? Third. So when you get your score, subtract from 100, that's how many points off of a perfect score you were. Divide by 3, and that's how many points you could get added if you perfectly figure out how to do the problems on the corrections, ask me or others, okay? Take your score, subtract from 100, divide by 3. Let me get an out person, and then we'll go from there. AJ, Nick, hey, Michael, Chris, Jordan. Oh, I'm sorry, I did not even go through the last name. Give me a second, I'll figure it out. Chris, Yamashita, Jordan, Jackie, Joyce, Ryan, oh, Ryan's not there. Sorry. Joel. I forget how many names I have. Rebecca. Jake.
I thought that was another 0.
Other Ryan. I found you. Valentina. Josh. Christine.
Look at that.
Jaden. Yes, there we go. Joe. Ryan. Vicky. John, hearing. Leo. And Chris. Pause. 100 minus your score divided by 3. That's what direction we'll get back. Alright, corrections will be due until next Thursday? Next Thursday, next Friday, something like that.